Hello guys, can you hear me well? Okay, excellent. So we can start. So my name is Kuba. Today I will cover some basics of recommendation systems in Ruby. All of the code will be handled in Ruby because I'm a senior Ruby developer at Netguru. However, all of these concepts may be easily portable to any programming language you use. So let's start. First, a little bit about me. I'm Kuba Nieszcza. I'm senior team and actually tech leader at developer. I was also a senior developer before, and I was mainly focused on Ember.js through my career at Netguru. But recently, I'm more focused on research and development and a little bit about machine learning. So in R&D department, we are trying to figure out how machine learning techniques can improve the experience of our customers and their products. And today I will tell you about one of the most commonly used machine learning technique in web apps, which is recommendations. I'm going to describe some theory behind it, a little bit of math, but it will be very easy to understand how to build your data set and how to code your first recommendation system. Okay, so first things first, what is machine learning? Actually, there are thousands of applications of machine learning, but we always have Wikipedia. So according to Wiki, machine learning is a subfield of computer science that studies computers' ability to learn without being explicitly programmed. So if we code some explicit rules about our recommendations, for example, if a user bought display, we offer him or her HDMI cable, then it's not machine learning because such code cannot be portable to any other category except the displays. So to create some technique that will be easily portable between all of the categories that we have in, for example, our shop, we need to use machine learning. So if we know what machine learning is, let's dive into recommendation systems. And actually, there is also a division. We have two types of recommendation systems. And first question, what is a recommendation system? Recommendation system predicts user responses to options. And this like a little bit hard to understand definition actually means that, for example, in e-commerce, we can recommend products that the user can be interested to based on his or her previous purchases. And we have two types of recommendation systems. Like two big divisions. First is collaborative filtering, and the second one is content-based recommendation systems. So what is what? Collaborative filtering methods are based on all the responses that all our user base gave in the past, and they try to collaboratively find out recommendations for this particular user. However, content-based recommendation systems are more based on classification of the items to particular, for example, category, and recommend other items from this particular category that the user might be interested in. Today we'll dive into collaborative filtering only, because it's, I think, most common way of recommending items in web apps. However, I strongly recommend you to see and check out content-based techniques also. And another division actually, because collaborative filtering also have types of recommendations. First one is memory-based, they're differently named user-based, and memory-based recommendation systems are based on finding users that are similar to the current user and calculate a weighted list of items that have not been ranked by this current user, which means that we take all other users, we calculate similarities between each user and current user, and we create a list of recommended items that were not ranked by the current user yet. On the other hand, we have model-based recommendation systems, which are actually calculating similarities not between users, but between items. And we take a list of items that current user has already ranked, and we recommend him other items that are similar to these items. These techniques have their advantages and disadvantages. Memory-based, user-based filtering is much more computational heavy than item-based, because each time we want to calculate a recommendation, we probably in most cases need to calculate all the similarities at the time of giving recommendation, because the similarities between users are changing quite fast. I mean, today I might be very similar to other user, but when I buy a new kitchen, I'm probably totally different. When item-based recommendation systems have this advantage that you can pre-compute the similarities between items earlier and store them, for example, in memory, and reuse them each time you want to make recommendation. So item-based might be much faster, but today we'll dive into user-based because they are a little bit simpler to understand and to implement. So I know that, sorry, you've seen my notes. I know that examples are a really important thing about learning new things, because they give you some motivation what we can achieve with what we learn. So I would like to share 3 examples of recommendation systems that I'm pretty sure you are all familiar with. First one is, of course, Amazon. Actually, one of the companies that implement recommendation systems in their web app first on the market. They recommended. Amazon recommends us items based on what we have already bought, what we have been watching in current session, or any items that might be similar to the item we are currently watching. Next thing is Spotify Discover Weekly, which recommend us a playlist of tracks based on the tunes that we have been listening to last week. So also a nice feature. And last but not least is Netflix, which recommends us movies based on the movies we have seen. And actually Netflix even offered a $1 million prize for anyone who is able to write better recommendation algorithm than theirs algorithm. So they really try to invest as much as possible into the recommendation system. Okay, so this was like a theory. The lightweight theory about recommendation system, and right now we'll dive into a little bit of math in recommendation systems. So let's assume we want to calculate recommendation for me, a recommendation of GitHub repositories based on the repositories that I have already stored. So let's assume that our dataset consists of a couple of repositories and a couple of users different to me. And we can create a matrix that represents which user, Bob, Alice, Dennis, or John, start which repository. We have 4 repositories and 4 users, and 1 means that Bob have start React, Alice start React, Bob didn't start Ember, but he start Vue.js, and so on for other users. We also have, let's assume that we have, don't ask from where, let's assume we have a vector of similarities, and this vector of similarities is a numerical representation of how much Bob is similar to me, how much Alice is similar to me, how much Dennis and John are similar to me. I know that these numbers might look like they magically happen here, but we'll dive into how to calculate these similarities. What we need to remember right now is that a similarity represents from 0 to 1 how much similar is user to me. So actually it looks like Alice is very similar to me. It has almost 1. However, Dennis is not similar to me at all. And if we do a simple math and we multiply this matrix with this vector, we will get something called rank. And this rank is actually the recommendation we want to have. The calculations are pretty simple. We take 0.88 plus 0.92, and this is recommendation for React. We take 0.92, 0.22, and 0.33, and this is recommendation for Ember, and so on. However, if we sort this rank to get like the most recommended repository for me, it will not be actually true. Because take notice that, for example, Vue.js has very high rank comparable to other repositories, but it is because of the fact that actually each user have started this repository. So to make this rank a little bit more true, we need to normalize it. So we normalize it, dividing the rank by count of users that took part in creating this rank. So the high result for Vue.js, which was over 2, is right now not so high. And we see that actually the most recommended repository for me should be React, because both Bob and Alice started, and they are both very similar to me. So the next question is actually how to calculate the similarities and how we can numerically measure how much am I similar to Bob, Alice, Dennis, or John. Let's say that we want to know how much is Alice similar to Bob, and we know that Alice likes Ember, Angular, and React, while Bob likes only Ember and Vue.js. And there are actually a couple or even tens of methods to calculate similarity between users. One of them are better with one solutions, and the other one are better with other problems. Today I will show you two similarity functions. First one is called Euclidean distance and is pretty good for, maybe it's not pretty good, actually there are better, but it's the most easy and quite good similarity function to calculate similarity between users that ranked something in range from number A to number B. Let's see an example. Let's say we don't have repositories. Right now we have movies that we want to rank, and we can draw a plane where y-axis is Bob and x-axis is Alice, and we can put the 3 movies that both of them have ranked on this plane. So we see Iron Man, and both Alice and Bob decided that Iron Man was like a pretty sad movie. They didn't like it, it was bad, so they ranked it 1. On the other hand, Bob really loved Harry Potter, so he gives 4 for Harry Potter, while Alice not so much, she gave 2. The Lord of the Rings was quite funny for Alice, but a little bit boring for Bob. So he gave 2 and she gave 3. And right now, based on the plane, based on this plane, we can calculate the simple Euclidean distance between the responses, which is for Iron Man 1 minus 1 square plus for the Lord of the Rings 3 minus 2 squared plus for Harry Potter 2 minus 4 squared, and all of this root square. This is any dimensional Euclidean distance where n is the number of movies that we want to rank. But taking this function as our similarity function is not a good idea, because this equation will give smaller results if we are more similar and higher results when we are less similar. And we actually want to have something between 0 and 1. So we refactor it a little bit, this equation, and with such equation, we will end with almost 1, exactly 1 when both users are the same, and very small near to 0 number when they are when the users are totally different. So this is a good representation, a numerical representation of how much two users are similar when we have a numerical range that they rank. Here is from 1 to 4. However, in our GitHub example, we don't have a numerical representation of the range of the repository. We only know if the user started or not. So it's a Boolean value. To calculate the similarity between Boolean values, we can use other similarity function, which is called Jaccard Coefficient. Jaccard Coefficient is a statistic used for computing the similarity between two sets. And if we want to calculate similarity between Bob and Alice, we can represent the repositories that they have started as sets. For example, Bob set will consist of first repository, third, fourth, and fifth, while Alice will have only first, second, and fifth. So if we take a Jaccard coefficient, which is equal to common part of these two sets divided by the sum of these two sets, you will see that the common part is the first repository and the fifth repository. So it is 2, while the sum of these sets is basically all 5 repositories. And the same here. So we divide 2 by 5, and the similarity between Bob and Alice may be described as 0.4. This is also not the best possible representation of similarity for Boolean values, but it's really easy to understand and is really easy to implement. So I've chosen this as our first recommendation. Okay, so before we move to see some code, what are the common problems for collaborative filtering? Well, first of all, it has cold start, which means if we don't have any users, we actually can't recommend anything. So we don't have any data to start with. Also, the scalability may be a problem because the calculations take time, and they actually really take time. I will show you later. We can use item-based recommendation, but it's not subject for today. So let's focus on this user-based calculation-heavy recommendation. And the last thing to remember is that the structure of our data set always have impact on our results. So sparse data sets give much worse results than dense data sets in collaborative filtering. And I think that a couple of you at least are asking what is sparse and dense data sets. So let's see. Sparse data set is when users have ranked only a small subset of available items. For example, if we have 3 repositories and 3 users, we can see that actually both Bob and Alice start only one of the repositories, while John didn't start any. On the other hand, dense data set is when every user has ranked almost every item. Sparse data sets are very common in e-commerce shop, for example, where we have like millions of products, and even though we may have millions of users, that probably common user only buys a couple of things and ranks a couple of things. On the other hand, dense data set, the example of dense data set might be Academy Oscars, Academy critics, and the movies that were nominated to Oscars, because probably every Academy member have seen every nominated Oscar movie. and can rank it in some range, either if you like it or not. Okay, so this was some theory and math behind recommendation engines in their basic implementation. So how can we create our own recommendation engine? There are a couple of blog posts, and actually there is a couple of videos also how to build your recommendation system in Ruby. And I tried to show you how I have built my recommendation systems using actually Rails and not only Ruby, because the very detailed blog posts about building recommendation systems very often base themselves on the fact that we have, for example, data in some array on hash, which is actually not a typical production case where most of the data is stored in database. So I will show you how to build and use Rails for this. So to create our own recommendation system, we need to define our goal and what data set we choose to use. Let's say that my goal is to recommend GitHub repositories based on stars that you gave. And my choice is to use GitHub repositories and Stargazer's dataset. And unfortunately, I don't work at GitHub, so I don't have this dataset. So my only possibility is to basically scrap as much as I can from GitHub API. So I check API, I need to know how it works. I need to understand the limits of this API. And then I need to write Ruby code or Rails code to scrap these repositories and Stargazers. And actually, writing a simple script might not be a good idea. I recommend to use something more fancy. I use Sidekick and Sidekick workers, and I will show you why. So when I understand the limits of GitHub API, I see that when we are not signed in, we can only make 1,000 requests per hour. If we are signed in, we can make 6,000 requests per hour. So I created a simple Rails app that all it can do was sign in via GitHub, and I asked a couple of my friends at Netguru to sign in to give me their tokens, and I created a quite simple but based on Sidekick algorithm to scrap first all the repositories that current user have starred, and then all the Stargazers, all the GitHub users of each of these repository. So it might have some kind of exponential growth. So I decided that probably it will reach limits a couple of times. So I decided to use Sidekick and make my Sidekick workers rescheduling itself when they hit limits. So basically, this is the algorithm that I described. I fetch user start repositories and then fetch all Stargazers for each repository. And if you spend at least couple of minutes to think about your scrapping system, you will end up with a couple of workers that initially are trying to schedule scrapping, which is fetch start repo scheduler. All this worker do is find user from token and schedule scrapping. The scrappers are fetching start repositories with pagination, and they are trying itself in the next 65 minutes to wait for the end of GitHub limits. After it's finished, this worker is scheduling a scheduler to fetch Stargazers from each repository, and again the scheduler is scheduling fetching Stargazers using pagination. I broke that to 4 workers because I created actually a pattern that is commonly used to work with APIs. I called it SafeGet, but probably most of you are familiar with it and maybe called it something else. SafeGet is basically a OctoKit get execution, but wrapped in begin rescue block to rescue from OctoKit too many requests. And if OctoKit too many requests happens, it reschedule itself to perform in 65 minutes, starting from the point where it finished. And very, very similar method to this is used in every Sidekit worker to fetch the GitHub repository. And I will also, in next couple of days, open source this whole code. So definitely you will be able to see all of the workers. It wouldn't be very readable if I put it here. So my key insights from creating this dataset is that I use Sidekick with a bare Rails app. It took 18 hours to grow 20 signed-in users. So that's why I recommend using Sidekick instead of simple Ruby code. If you don't want to have your computer running for 18 or more hours, then definitely it's better to deploy it somewhere. During these 18 hours, it created 3.5 million relations between stargazers and the repository, but only 1,000 repositories. That's why our data set is extremely sparse, which I will also tell about later. What is more interesting is that it reached the limits over 200 times. So if we don't make sure that our scrapping system is bulletproof, it won't work. We need to handle the limits. And actually, the massive number of this relation, 3.5 million compared to only 1,000 repositories, becomes from the fact that most of these stargazers are people that start repositories like React or Airbnb. So for example, if my mate from Netguru have started React, then I will try to get all the stargazers of React repository, which is like a couple of tens of thousands. And for example, and the same for other most start repositories. So as I've said, we have quite huge data set to start with, but it's very sparse. We won't do anything about how to fight with sparse data is like the subject for another presentation. But we just need to know and understand our data before we evaluate the results. And because of the fact that we are using Boolean values as start or not start, I use Jaccard Coefficient. This calculates some similarities function method that takes 2 arguments. It takes an array of stargazers, let's say users, or better use stargazers, an array of stargazers IDs that we want to compare to our current stargazer ID. We want to calculate the similarities based on the repositories that these stargazers start. So we first create an array of the repositories that the current users start, and then we iterate by stargazers that we want the current user to compare to, and we create an array of the repositories that each of these users start. And the next step, which actually could be done in one step, but in the next step, we are, for each of the stargazers, we are calculating the similarity between the subject, so our current stargazer, and the repositories of the stargazer we are comparing to. So the Jaccard coefficient is taking only 2 arguments. It takes first array of IDs that we start, and array of IDs that our user that we want to compare to has starred, and it gives the results. Last, we just sort them by similarities. This implementation that you see here is not good. I mean, it is based a lot on active record, and in current state, what you see, this can take up to 2 minutes for one user. But if we skip active, we move more calculations to memory, for example, by fetching 10,000 of users in one batch, then it is much faster. And today I managed to optimize it to 7 seconds from 2 minutes per user. So 7 seconds is not so much, but it's computation heavy actually. So we have an array of similarities between users. So we have an array that represents a similarity of each user between each user and me. So how to recommend right now any repositories. To calculate recommendations, we need to iterate by each user that we have similarity between me and this user, and do a multiplication between the matrix and the vector, which actually in Ruby code looks like this. We first create or take if created. Actually, not a good idea. Oops. Where is the rubber? Doesn't matter. I can't find rubber. Okay, so we create an array of repositories, and we have a field called total and the field called count. The count field will represent the number of users that took part in this recommendation, while total will represent the sum of some similarities that took part in this recommendation. So this is exactly the same thing that I have shown you before. I would like to come back there. So we are taking the count of similarities, which is, for example, Bob plus Alice, and we divide it by count of users that took part, which is 2, Bob and Alice. So getting back to the code. So we create an array, a hash actually, in this case. We create a hash of repositories where the keys are basically an ID of repository, and the object in this key has 2 values, total and count. And last but not least, if we iterated by all the users that are similar to me, we sort recommendations by the result of recommendation total divided by recommendation count. And actually that's all, because if we sort the recommendation array by this result, it will give us an array of repositories to recommend sorted by the most high rank, which eventually only means to output the repositories that are in this array. So to sum up, first we calculate the similarities between users based on array of IDs of the repositories that our current users start, and the array of IDs of repositories that each user start. We sum similarities for each user that start particular repository, and we count how many users actually start this repository. And we sort by result of this division. And actually, out of this data set, this is a recommendation result for myself. I recommended 10 repositories to myself, and actually I put stars next to the ones that might be interesting to me, actually. So this basic algorithm has recommended me 10 repositories, but only 4 of them are interesting to me. So it's not a really successful recommendation engine, but it's a good place to start with and to tune it to give better results. So to sum up, I think that collaborative filtering is not as hard as you might think, and actually recommendation engines are not as hard as they seem to. Um, Next thing is that we should always remember that we should test multiple similarity function to find the one that fits our purpose. These bad results of recommendation, I mean, not very bad, but not also not very successful, may be caused by the case that Jaccard coefficient is not really good solution for our problem. Maybe we should try a couple of other similarity functions to see how they work. Maybe even we should find another way of normalizing our rank, not by the count of user, but something else. But it's all the case to tune. It's all about tuning your algorithm, not inventing from scratch. Um, Next thing is to always analyze your data set, try different approaches, try to make it denser. For example, from our 700K of stargazers, we can remove all of the guys that recommended only a couple of repositories. Let's take only users who at least start 10 repositories into consideration. This will make our dataset a little bit more denser than before. And last but not least, don't be afraid of scaling unless you need real-time solutions. And like the best example for this is what I have already said is that in the beginning it took almost 2 minutes to recommend a set of repositories. Right now it takes less than 8 seconds, only because I spent a couple of minutes actually to try to optimize it. And I also put some external sources that are quite good, in my opinion. First is that machine learning is way easier than it looks from Intercom. There is also a very good blog post about creating simple recommendation system in Ruby that shows you how to build the code step by step, so a little bit better than me, but it definitely takes more time than only 30 minutes to build this recommendation system with this blog post. But it's really nice. However, it doesn't cover how to fetch the dataset, so I hope that my tips might be useful for you. And the last thing is the video. People who like this talk also like building recommendations. Also very nice. A lot of common problems, a lot of math behind, and a couple of other similarity functions to check out. And basically that's all. So thanks for listening to me. I love to ask any questions that you have that I know the answers. I see that a couple of people is typing, so. So Michał asks if I think that recommendation systems are good for putting items into categories. Actually, I don't know. I wouldn't do it. I would rather check out other classification methods instead of recommendation systems, instead of collaborative filtering, because it also depends on data that we have. If we have a data about every item, for example, the description, photos, and the details, and so on, I think we can create much better categorization based on these particular features of each item than on the responses or previous purchases of our customers. On the other hand, if we don't have such data, if we don't have particular features of each item, then definitely the collaborative filtering is the last thing that we can check out. So it depends on the data you have, but I would rather try to use features of each item. And Lukasz is asking, great presentation, thanks. Question, have you used more complex methods like SVMs or KNN? I've checked out KNN, but not in this particular use case. I've used KNN for calculating actually the similarities between Netguru employees based on their skills, but the results were a little bit, I mean, they didn't represent actually any good structure behind this data. I've used SVMs, but only in image classification. I haven't been using SVM in recommendation system nor web apps. Mikołaj, have you tried to find using more categories on recommended repositories than stars, like language, backend, frontend technology, and so on? Yeah, I didn't try. I think that it's a very good idea. I mean, this is one of also my ideas to improve this system and to check out how it might affect results. I haven't done it yet, and I think that actually you would need to drop collaborative filtering and use some kind of other algorithm to take both matrix of matrix of stars and the features of each repository. It is a little bit more complex than simple collaborative filtering. But I think that it is a good idea to take these features into considerations. Also, I think that it will be also good to take the timestamp of star into consideration, but it also is definitely more complex than simple recommendation system. Valenty proposed to use BigQuery from Google. Actually, maybe I haven't heard about this. I haven't checked out BigQuery. If they have GitHub base, then it looks good. I will check it out later, definitely. Thanks. A guy who works at my competitor asks if that I told not be afraid of scaling and how fast it should be for such type of tasks. So would you get significant performance boost if you would use faster language and connect recommendation engine to RaceUp? Definitely, I would get significant performance boost, but it depends on my code actually. For example, out of these 2 minutes that took the recommendation to calculate, I optimized it to 8 seconds only by making better SQL query and not using active record. So I optimized it like 17 times only by making better SQL. And I think that I can optimize it even more. And definitely Elixir or Go would be much faster than Ruby, but I don't think that you will see a significant difference by a human eye. On the other hand, it depends on what actually you are calculating. This recommendation system, collaborative filtering, it is actually only multiplication, so it's not a really there is not a very low multiplications comparing, for example, to SVM. So it's not a huge deal, I think. However, I would never recommend writing SVM training machine, for example, in Ruby. Definitely, it's better to use Go or C++ or something like this. And I told that we shouldn't be afraid of scaling, but not in terms that we can scale up to infinitely. I meant that until we need a real-time solution, we don't need to be afraid of this. Łukasz is asking if we are using any kind of machine learning system in the production, in any of our products. No, right now we are not using any machine learning system in our customer products. We are researching it and trying to learn some how to actually implement these algorithms. And this recommendation system based on GitHub stars will be our maybe first, maybe second. It depends how fast we finish it. Production ready product in Rails. However, as it is using a sidekick for calculating recommendations, I will try to move it out of Ruby, either to some microservices, or maybe I will use AWS Lambda. I don't know. We'll check out later if it's getting if it makes a problem. Okay. I think that there is no other questions. Nobody is typing for a while. So, okay, somebody is typing. Okay, thank you. So I think that this is the end. I will try to make sure with Marta that we have sent you, or somehow maybe make it available on our page, on our web page, the code of these examples when I finish them in a couple of days, I think. And I will also try to create a blog post out of this webinar that I've shown you today, to make it easier to follow code and write your own recommendation system. So stay tuned for later. Thank you, guys. See you.